Um, so using that spatial temporal model, what stock assessment historically has needed is an index of abundance, so the sum across space of a spatial temporal model's estimate of density. And if we sum that across different footprints, we can get on the right the total across the whole area in red with a plus and minus 1 standard error. The green is the conventional footprint of sampling where the stock was believed to be historically. And the blue is the estimate in the northern portion that used to be dominated by sea ice and has not been in the last several years. And we can see that the model estimates a rapid increase in the proportion in this northern unsampled area with correspondingly larger standard errors in times when we weren't sampling it. What's more interesting, I think, for our purposes here is that, with this model-based framework, we can also estimate, questions that are interesting for spatial ecology. So if we look at the northward center of gravity from its southernmost estimated point in 1995 until 2018, it's moved almost 300 kilometers north over, a little over 20 years, but also since I think that's 2012, it's moved almost 200 kilometers north. So in about 5 years, moving 200 kilometers north, I think is some of the fastest climate-driven shifts for any species I've seen documented. And this happens to be the species, the stock that was that drove the way that fisheries policy and legislation is constructed in the U.S. We can also back out effective area occupied and other interesting metrics of spatial ecology. So before moving on, thanks to Jimmy and Ellie, who has included this in the stock assessment in 2018 as an alternative model. Thanks to Stan and Bob and Mike Sigler, who led to resampling that northern portion, and the many scientists and ongoing support for the Lhasa Sea Ice program. So that's the first of 4 pieces I'd like to cover. The next is about essentially another rationale for model-based estimates of distribution shift, and this was published in Methods in Ecology and Evolution of 2016 with Malin, who I believe spoke with you earlier today. And again, the rationale being that, obviously, anthropogenic changes are driving distribution shifts worldwide, and we need an efficient way of measuring those in an unbiased way across regions. And in this paper, we compared 2 different metrics. One of them is this abundance weighted average that many analysts have used over the years. It's essentially the weighted average of the location of sampling weighted by the amount that's seen at each location. And the alternative that I think is more appropriate in many cases for global and comparative analysis is what I call a species distribution function. So basically fitting a spatial temporal model and then taking the sum or the integral across that density function to back out metrics of distribution. So the abundance weighted average metric is shown on the left. Again, it's just a weighted average. And there's several downsides to it. One of them is that it's biased when the spatial or temporal distribution of sampling changes. It also confounds differences in the distribution of sampling due to randomization and has other issues. And so in the west coast of the US, we have sampling from 2 different programs from 1977 up until present date. However, in the 70s and 80s, the spatial location of sampling was not standardized, and also the date has changed over time. And so, for instance, in the top panel on the right, 1977 went all the way south to the coast of Mexico, but the 80, 83, 86, and I think those, 80, 83, and 86 didn't go as far south. And so kind of a naive analysis of these data would end up concluding that species moved north over those years, even though it's just the average location of sampling that's moved. So as I said, it confounds shifts in sampling with shifts in distribution for the things being sampled. It can't control for any variables, so it can't do any counterfactual testing of what would have happened without fishing. It can't correct for differences in gear or timing, and so on. The alternative is this species density function approach, is what I called it in that 2016 paper. It's a spatiotemporal model that estimates a density function d as the product of encounter probability and positive catch rates r, the expected catch rate given that it's encountered. And then, somewhat obviously, you can back out, spatial metrics like center of gravity in that first equation, or in this case, in 2016, I was using what I called kernel area occupied. So, like Mathieu Wallet has some work looking at, I think he called it inertia, and it's essentially a measure of the covariance if you approximate the density function, and you can use that to define an area occupied measure. So I became interested in this after Malin Pinsky's 2013 Science article, which maybe he presented earlier today. I think it was a tremendously impactful and useful study. However, I was somewhat baffled about the results published in that paper that the U.S. West Coast is moving southward. The example shown in the main text of that paper showed Raja binoculata, which I had studied a bit and had no reason to think was moving south. And I actually couldn't think of any individual species that was moving south. And so it didn't make much sense to me to conclude that the community as a whole was moving south. And so, and furthermore, another problem with this abundance weighted average is that you can't separate interannual variability from long-term trends. There's no, typically the way it's done, at least in the past, is, to back out abundance weighted average and then fit a linear trend to it and summarize some linear trend and distribution. And if you look at a species like Pacific hake, that one of the more commercially valuable offshore species on the West Coast, the distribution function varies a lot between years in a way that is probably important. So we know that this species, when it has, when the juveniles are typically, recruit to the southern portion of the California Current and move northward over the summer, the story is, where the amount they move north depends on size. And so times when they have a strong cohort come in, that'll typically cause the population to be skewed southward. And so you can actually see cohorts coming through in terms of their spatial distribution. And so if you look at this on the left using an abundance weighted average and just plot the naive, estimate that isn't corrected for shifts in the spatial distribution, then you fit a linear regression to that, you get this southward shift. Whereas if you do a model-based estimator that corrects for differences in spatial distribution, you get what I think is a much more interesting story about decadal scale shifts in the distribution that drives decadal scale shifts and availability to different fishing ports, as we are analyzing now in a paper in review at +1. So we did a simulation experiment, and under 4 different scenarios on the left-hand side, looking at the centroid northward center of gravity, the gray shading is the width of an interval representing its location across all of the simulation replicates. And then on the middle column is the estimate and across all those simulation replicates of the blue, the abundance weighted average measure, or the red, the model-based measure. And then finally on the right column is bias in that centroid. On the right, you can see the story is that, the abundance weighted average is biased northward in those years when sampling did not go as far south, and that's, fairly obvious that we wanted to make the point firmly. Whereas the model-based estimator is not exactly unbiased, but it does do a much better job. It minimizes that bias, I think. And so if you look across different stocks, another concern that comes up is whether you can back out movement from one year to another using this model-based estimator. Is it too complicated of a story if you look at interannual variability? And so instead of fitting a linear regression, in the model-based one, we just take the first and last year and take the difference. And we get, in some cases, a much more precise measure out of a model-based metric because, well, for several reasons. So I still think that you can back out useful inference from the model-based one about trends in a way that also characterizes interannual variability. And in a lot of cases, the abundance weighted average ended up being significantly southward, even though the model-based one estimated at least either a stable or a northward shift. And so the abundance weighted average, I was able to replicate Malin's, Malin and Hall's result, while also noting that I think it's biased due to the particulars of sampling in that region. This is the same thing again, basically saying that, if you plot a linear regression on center of gravity, you not only get a biased measure for the West Coast, but you disguise significant interannual variability, and then you can get similar inference out of the model-based measure. So based on this, my recommendation is that we as a community, when trying to do global analyses of distribution shift, use a similar method that is robust to changes in sampling distribution. I have a lot of sympathy to Malin, and it's a case in any meta-analysis that you by nature are not going to have as much specific detail about each individual sampling unit, each individual region. And so that's why I think it's especially important to try to come up with estimators that are, pretty reliable across the circumstances that we deal with in fisheries when doing comparative analyses. So that was the story for the U.S. West Coast. Next, I'll spend a few slides on what's happening in the south coast of South Africa. Sorry, this title is a typo. This is work that's been led by Jock Curry, who's a PhD student who recently graduated in South Africa and now works for their fisheries management institution. And Henning Winker was, I got to know them through Henning Winker, who works for the Fisheries Science Agency down there, DAF. And we've had a lot of collaborators there. So there's two different surveys of the Agulhas Bank off the south coast of South Africa. There's a spring and a fall survey. And I think that's an interesting question about, that hasn't often been looked at in the literature as differences in seasonal distribution shift. So, for instance, the Northwest Atlantic of the Northeast Fisheries Science Center has two different seasonal surveys. Korea has two, and so on. ICES obviously has several. And when I see people publish work on distribution shift, I haven't often seen analyses of multiple seasonal surveys simultaneously, or what it means when they differ. There's also some differences in bottom trawl gear that we explore in cases where we subset the data or fit a model with estimates of gear shifts using intercalibration samples within the model. And it runs 1986 to 2016, so it has a good time scale for 44 commercially caught species. So the new piece that Henning suggested was taking, in this case, this is for Diptera. Well, slime skate. I don't know anything about the individual species there. But in this case, we plotted the spring in blue and the fall in black, point estimates and 95% confidence intervals for each year. And then Henning has a Kalman filter, a multivariate Kalman filter smoother that he fits to these to look at distribution shifts. And the nice thing about the smoother is that, of course, it reduces to a linear trend in cases where that seems appropriate, but it also propagates information about, with interdecadal variability for species when that seems important. So in this case, this species, appears to be shifting somewhat southward, although, it's only maybe significant, for the, east. I guess it's significant for eastward shift in the fall, but not the spring. Doing this with a multivariate Kalman filter, we can back out sort of, a useful measure of, community-wide distribution shift across those two seasons, and we end up with an estimate of 2.6 kilometers per decade. So a much slower distribution shift than has sometimes been published. There's also a change in effective area occupied of 62 kilometers per year, and this, like many, ends up having a total sampled area of 200,000 square kilometers. So that's not a tremendously large rate of decline in effective area occupied. But both of those are estimated to be significant by the Kalman filter. So these, in summary for Algulas Bank, distribution shifts are often not significant for individual species. 6 have a significant shift west, 3 have a significant shift east, which means that the remaining 35 do not have any significant shift estimated by the Kalman filter. Area occupied has even fewer significant shifts, but two of the 3 that are shifting significantly show shrinking area. And the headline results is fairly low rates. If I was there, I'd love to discuss, and if we have time, I'd love to discuss the file drawer problem. So in meta-analysis, generally there's a concern about publication biases towards interesting results and also publicizing interesting results. And so I do think, personally, based on my work, that there are regions where spatial shifts are occurring slowly, and we can come back to that later if we have time. Finally, I picked out one global meta-analysis just to highlight that we can do meta-analysis using these model-based measures. So this was published in the Proceedings of the Royal Society B in 2016, again with Henning Winker, Anna Rindorf, Jin Gao, who's now at Memorial, and Dana Hanselman, who works at the Alaska Fisheries Science Center. So for this, we compiled data for 6 different regions worldwide, including the North Sea, using the DATRAS web portal, and working with people at Danish Technical University to convert to biomass for that area. So there's different amounts of sampling for each region, but 6 seemed like enough to start evaluating comparative analyses across regions and across taxa and spatial ecology. So the question is, what is the average relationship between abundance and effective area occupied? In my education, I was brought up talking about Alec McCall's basin model. A terrestrial ecologist might call this density-dependent habitat selection. But the point is that we fit a spatial temporal model to data for 20 stocks in each of those 6 regions. We extracted an estimate of abundance, effective area occupied, and their covariance in each year. And then we fit a second stage meta-analytic model to data for those 120 stocks and estimate a slope between the log area and the log abundance. And that log area, log abundance slope is a nice metric because it essentially partitions how much of a given change in total abundance is due to increase in effective area versus increase in density within the area occupied. So if that slope is equal to 0, it's what I call the proportional density model, where proportionally density increases in an occupied area, but it does not spill out at all. If the slope is 1, it corresponds to a case where density does not increase in core habitat at all, and only abundance changes only result in spilling in and out, and the intermediate looks intermediate between those. So when we do this for 120 stocks, we can see cases where there's both a positive and a negative slope. So a positive slope, for instance, looks like arrowtooth flounder in the left-hand column here, arrowtooth flounder in the eastern Bering Sea. So in this case, arrowtooth flounder over, and again, Paul, I think, has studied this much more extensively. So feel free to jump in, Paul.
That's good.
Thanks. My 30,000 foot view of this story is that arrowtooth flounder over time has spilled from, the deep, the slope, either increasing in abundance or moving onto the shelf more. And in either case, its total abundance in this eastern Bering Sea footprint has increased at the same time that it's expanded in range. And so looking on the right-hand side, if we look at the index of abundance and the effective area for arrowtooth flounder, we see a substantial increase over time in the index of abundance and sort of a spotty but noticeable increase over time in effective area occupied, resulting in a slope of 1.75. So that 0.175 means that for every 10% increase in total abundance, we expect a 1.7% increase in effective area occupied. By contrast, Little Skate in the Northwest Atlantic over time has showed a pattern where elevated abundance shows up in small hotspots, small isolated subsets of its typical distribution. And so, in fact, when abundance is increasing for arrowtooth, for Little Skate, it typically has had a lower effective area occupied, resulting in a negative relationship, an estimated negative relationship in this case. So the meta-analysis is to estimate this log slope, and we do this while trying to account for the biases that are typically associated with using model output as data. So specifically, we extract the estimated covariance in our estimates for each year for a given species. And then we estimate an additional variance component. So that's shown in that sigma sub k piece. I'm not going to walk through the notation very much, but the covariance includes both process error around this slope as well as measurement error that we propagate from the first stage of the meta-analysis for each stock and year. If we do that, the headline result is that we end up finding a statistically significant but biologically weak average effect. So my memory is that it's about a 0.06 average effect. Representing that on average across stocks, a 10% increase in abundance leads to a 0.6% increase in effective area occupied. However, there's substantial variability among species in that relationship, and again, out of 120, 14 were significantly positive, and the majority did not have any significance when doing a Kirkle-based estimate for individual stocks. If we do that looking at individual taxa and individual regions, there's also substantial variability among regions and taxa. And so the predicted slope is strongest for gadiforms, and it's strongest typically in the eastern Bering Sea and the northwest Atlantic regions. Let's see. The eastern Bering Sea. So the eastern Bering Sea, on average, a cod in the eastern Bering Sea is expected to have 0.2 relationship indicating a 10% increase in abundance leading to a 2% increase in effective area occupied. Other regions like the Northwest Atlantic had essentially no relationship on average for cod, and so on. So, what do I take from all of this? Well, some of this we'll talk again about tomorrow, hopefully. But I think that there's a substantial and very interesting question about variability among regions, among taxa, and across time. So, among regions, for instance, the Eastern Bering Sea is rapidly changing recently, and I think over the 30 years has shown itself to be very dynamic in terms of spatial ecology. South Africa, by contrast, is changing very slowly. The west coast of the US is changing very slowly. And it would be great to have more regions included so that we can improve our sample size for regional meta-analysis to really look at oceanographically what underlies these differences in spatial ecology. GADIDs show the strongest basin model and anecdotally seem to shift in spatial distribution very quickly. Rockfishes generally show a very slow response. And again, some of this makes sense based on basic life history theory. But the life history, the 80s style life history theory I've seen, it typically includes spatial ecology. So expanding our kind of conventional life history theory to include predictions of spatial ecology and responses seems important. And then finally, I also think when reading the literature about distribution shift, I think it's really important to think about whether studies accounted for sampling changes. Did they only look at the Eastern Bering Sea, or did they include response of spill in the Northern Bering Sea? Did they account for changes in sampling design, like in the California Current? And did they look at a single season snapshot, or did they account for all of the information across seasons, like we tried to do in South Africa? That's my last slide. Thank you, everybody, and maybe we have 5 minutes for questions.
Yep. Okay, thank you, Jim. We're just, we are distributing our microphones amongst the people who will want to ask questions so that their questions can be captured on our electronic lecture capture software. So we'll keep with tradition, and I'll allow Tom the first question, and just remember to introduce yourself.
Jim, hi, this is Tom Helser.
Hey, Tom. Yeah, good to hear from you.
I have a lovely view here. It's getting dark, though. You might have mentioned this, and maybe you didn't, but maybe it was implicit in the modeling. So you're dealing with multiple species and different ecosystems captured by different gears and different spatial and temporal domains of data. Is there any way in the meta-analysis construct that you can kind of assign some sort of weight towards an individual data point being robust versus another? Like, isn't there a variance that you can assign so that you're weighting more better data more heavily?
Well, that's interesting. Yeah, so Rainer Froese and I worked with Rainer a bit on meta-analyses to include in Fishbase, and we always, he's at times put in different kind of qualitative measures of study quality, and that was, for instance, that's now included in the Fishbase estimates of weight-length relationship parameters. So yeah, certainly there's ways to do that in meta-analyses. I didn't put that in a priori in any of these analyses, but the spatial temporal model that we're using does allow you to estimate different variances for different gears. And so I suppose if you have intercalibration samples, the model could identify on its own which ones it thought had higher, lesser variance.
Right. Kind of like an effective sample size sort of thing.
Yeah. Yeah, and then I should say that spatial temporal models are developing very quickly, and Casper Christensen and others at Danish Technical University have come up with some really interesting statistical measures of leverage that I have not used extensively. So, if we had more funding to do methods research, that would be an important direction to go.
Thank you.
Jim, I have a question. It's Tara. So you have done work in South Africa that you summarized, and you conclusion is that it's changing very slowly. What is the sort of environmental regime that those species are living in? We think of it as in an upwelling system, so does that make it more complicated?
Yeah, so I should say that my history as a researcher is looking at bottom fishes, demersal fisheries. And so all of the meta-analyses I've done are using bottom trawl data. And so, typically, it seems reasonable to me to believe that the pelagic system would be more, dynamic. And I don't know how much that upwelling, differences in upwelling would drive a difference in variability for the pelagic versus demersal systems there. I also, again, I was just studying the Algulas Bank, with Jock Curry and others, and I should have put a map in, but that's specifically in the south coast. That the west coast, with the two hakes there, is for instance, I think is much more spatially dynamic.
And there's no work that's been done there because it's upwelling systems are very interesting as a strong contrast.
Yeah, and I hope that we can continue this relationship with DAF through Jock and Henning and others, and clearly, a group such as yours is trying to reach out to different groups, and I think they've been tremendous collaborators. So I hope that if there is any comparative work coming out of this workshop, that we can, make an honest effort to reach out to them and include them.
Yeah, we did, with respect to growth databases, we spent a bit of time contacting people to see if they had age length data, and all of our investigations led to a similar conclusion, was that they didn't have long time data sets, that they had discontinued aging fish because it was proving very difficult. But your work obviously shows that they do surveys and that distribution is still an option for looking at responses.
Yeah.
Anybody have other questions for James while we've got him? And the coffee's going to be a little bit gone yet, so we can, okay, Paul.
Hey Jim, this is Paul. I'm sorry you missed Malin's talk because it was kind of on a similar theme. And one of the things Malin has looked at is how species traits affect movement and distributions. So he's kind of done some work looking at that. But have you thought about that? Do you think do you have any sense that there might be some traits that would be kind of some kind of predictors that would allow you to kind of generalize which stocks or which species you might expect to move and which ones you might be expect to be more static?
Yeah, so I'd love to do that. A parallel effort that I've been involved with is this meta-analysis tool called FishLife that does, assimilates life history information in a multivariate phylogenetic predictive model. And I'd love to, currently we're assimilating stock recruit data. I'd love to bring in spatial ecology metrics and use that to predict across all described fishes. My feeling is generally that there's a substantial story in terms of life history covariance. It hasn't always been reliably conveyed in the literature. So for instance, Charnoff talks about a Beverton-Holt life history invariant of M over K that Beverton and Holt never actually claimed. There's significant phylogenetic variation even within those patterns. And so I really think you have to put it in both a kind of phylogeny and trait context to get a good predictive story.
Paul mentioned Malin's presentation. These are being captured, so at, almost by the end of the day, they should be available somewhere. We'll have to, yeah, just click on the link in the Excel spreadsheet, right? And you should be able to access the presentations that have been given today in case you're interested. And of course, yours will follow in due course. I know we're going to be speaking with you again, but we're going to be asking all presenters to summarize their main points in their presentation in a short document that can be included in our final report. And I know that you've got a lot of publications, but maybe if you could synthesize essentially the 4 different studies that you've presented here, and they're highlighting the points that are very relevant to synthesis on a global basis. So that would be really super helpful.
Yeah, thank you, I will.
Yeah, that'd be great. So any further questions?
I have one more.
Okay.
Hey Jim, this is Tom again. You mentioned hate in your talk, actually in several talks, and I don't recall exactly what your metric was for, the northward extension of that population cluster or whatever that metric was. I can't remember now. But if you treated hate, for instance, in 2 different life stages rather than sort of one, full suite of ages, would you conclude that, the population had a northward distribution or shift significantly more than, what it would have?
Yeah, so I am really interested in those life, in Malin as well, in size and stage and age structure and spatial temporal models. And, I've got a fish and fisheries paper I did with Stan Kotwicki and Jimmy and Ellie that's in press, where we did that for pollock. And you can, once you have a population, structural model, you can do these attribution questions. You can say how much of the observed variance is due to the environment versus fishing versus, stage structure. And, Malin probably said this too, I think that climate attribution is a key tool in extreme weather event attribution, and IPCC wants probabilistic statements of attribution. And for fish, so much of what we see is size and age structure, and it makes a lot of sense for us to move as a community towards, stage structure distribution. In terms of hate specifically, I bet it would explain a portion of variance, but I wouldn't want to speculate how much.